All right, you are now at the second half of the fifth part out of seven, right? Of the Steady Flow Devices series. I thought about uh, mashing this up into, or sorry, dividing this into two different parts because, well, this is the basics of fluid movers, right? If we think about it, well, this sounds very understandable, very easy. But in this case, now for problem six, if we're going to think about problem six, this is a bit more involved because we are back with air. Air measuring 27 degrees Celsius, 100 kPa, and a volumetric flow rate of 0.25 meter cube per second is run through a compressor at steady state. Okay. The exit air flows at 70, oh no, 70 meters. Oh, I remember this. The exit air flows at 70 meters per second, and the exit pressure is 10 times the inlet pressure. If a polytropic process, which is n equals 1.3, is known to occur, look, it's not adiabatic anymore. It's not isentropic anymore. Something is going to happen. Determine, letter A, the exit diameter in centimeters, the mass flow rate, letter B, in kilograms per second, letter C, the compressor work, and letter D, the heat transfer in kilowatts. So let's just get on ahead. There are going to be a few things in here that change, especially because we're talking about air now. And because we're talking about a polytropic process, a lot of things are going to have to happen. Okay? Let's go ahead. Let's measure, or rather, let's take into account that this is air. A lot of things are now possible, right? A lot of things are now possible. And well, a lot of the formulas can now be changed. Okay? Suffice to say. So now this is your state 1. Your state 1 has your temperature 1 at 27 degrees Celsius. So that is 300.15 Kelvin. And then your P1 is 100 kPa. So there you go. That's good. Wait, let me see. It's getting late into the night. I don't want to get anything wrong. 300.15. And then there is a flow rate, a volumetric flow rate of 0.25 meter cube per second. Okay? It's run through a compressor at steady state. The exit air flows at 70 meters per second. All right. Ooh, all right. This part right here. This one is the very, very maddening one. Exit air flows at 70 meters per second, and the exit pressure is 10 times the inlet pressure. Well, in this case, you will have, or what I... Hold on. All right. Well, now you know a little bit of a preview as to when I am recording this. Yeah. Anyway, all right. Now we are at P2. There are two ways for us to take note of P2. Right? They said that the exit pressure is 10 times the inlet pressure. Someone might just get the urge to, you know what, 10 times 100, right? They said mise en place, right? 10 times 100 kPa, that's going to be 1000 kPa. Yes, I understand that, right? But I'm also reserving the right to just spell it out as just 10 times P1. Okay? What will that do? Maybe we'll just see it later. Okay? The exit air flows at so on and so forth. The polytropic process occurs. Now note that this is no longer an adiabatic process, an isentropic process wherein your index is supposed to be 1.4, not 1.3. So something is going to go wrong. Not wrong in the sense that like something's going to explode, but more like something has to not be cancelled. Something has to be a little bit more complicated. Such is the real world, right? Determine the exit diameter in cm, the mass flow rate in kilograms per second. Let's take note of all of this. Acquired, right? The exit diameter, so D2, right? The mass flow rate, your m dot. Your work transfer, WC, and then your heat transfer. Okay, there you go. And then you stop to think, wait a second, heat transfer. Yeah, Because, right? Because, okay, let's just write it down, right? Q minus W, delta KE plus delta PE plus delta H, right? Because ideally this should have been isentropic. You could have before canceled Q, right? You could have canceled KE and PE as well. But the thing is, two of the things in here you can no longer cancel. Why is that? Let's just look at things a little bit more critically, right? Solution. We're a bit too cancel heavy right now. There's a cancel culture. Ha ha ha. Right? The thing now is, well, it's supposed to have work. So we can't cancel the work. All right. And the thing is, as much as I want to cancel your KE, there was a velocity that was mentioned. So I can't do anything, sadly. There is going to be a change in KE in here unless I am sure that the vel1 is 70 as well. So in that case, well, there's no change in kinetic energy. However, there's nothing said about the elevation, so it's going to be delta PE is equal to 0. The thing is here, I also cannot cancel your Q because it's not an adiabatic process. It's not an isentropic process. So I don't know if there is Q. I don't know if there is no Q. Most probably there is. I don't know how much. And just like what we've said before for topic 2, it's usually the last thing that you're going to see. So how are we going to do this? There's so many things that we need to jump through first. What is W? What is delta KE? What is delta H? So let's try and break down these three big dealers right here. Right? We have first W. You might say, wait a second, how am I even going to start with W? Well, a little clue is there's a W. This is a steady flow system. So, okay, that's a steady flow work. All right. What about? Well, that is a steady flow work of a polytropic process. And so these things connect, and then you zoom out and you say, wait a second, I can go back in here. The polytropic steady flow work, right, is going to be N times P2V2 minus P1V1 all over 1 minus N. So we will bring that information with us to topic or problem 6. We will now say, aha, I now know what's supposed to happen. P2V2 V slash 2 na tayo, ha? V slash 2 because we don't have a volume, we have a volume flow rate. Minus P1 V slash 1 all over 1 minus N. But then you stop. Wait a second. I don't have a value of V slash 2. Aw. Sorry. I don't mean to, I don't mean to say that very dispassionately. But the thing about this is that you can actually get the value of V slash 2. How? Well, it's going to go like this, right? You have here a P1 and then a V slash 1. You have here a P2 and, well, you don't have a V slash 2. You would like to have one. And, well, there's actually a relationship between P1, V1, P2, and V2. It's been staring us right in the face. This N equals 1.3. Because this is a polytropic process that they've described, PV raised to N is equal to a constant. It does not matter if it is V or V slash whatever, right? This means that your P1 V slash 1 raised to 1.3 is going to be equal to P2 V2 V slash 2 raised to 1.3. Okay, cool. Now what? We can actually get the value of V2 in here already. Okay, let me, if you guys want to shift solve, go ahead. I will not want to shift solve. I would want to solve this manually. So I will put the P2 down. And what I will see in here is that V2 raised to 1.3 is equal to just V1 raised to 1.3 times, right? This is now your P1 all over your P2. So that means that if I raise both sides to 1 over 1.3, right, we will just get the value of V2, which is equal to just V slash 1 raised to times P1 over P2 which is now 1 over 1.3. Okay, so your V2 apparently is going to be V1. So that is what again? 0.25. 0.25 cubic meters per second times your P1 and your P2. Notice what's going to happen. P1 is just P1, and then your P2 is 10 times your P1. So what I can see, or what I can do in here, is just cancel. Raised to 1 divided by 1.3. You will get an answer which is raised to 1 divided by 1.3. Your answer will be 0.0425. 0.0425 meter cubed per second. So that is now your V2. Technically, you now have everything in here for you to be able to convert or get your answer. So let's just put everything together. We will have N is 1.3 times P2 V2. Your P2 is going to be, what again? 1,000. There you go. Times V2. Your V2 is, we just put this earlier, 0.0425 minus P1, which is 100, times your V1, which is 0.25, all over 1 minus 1.3. Okay, so this is your work of compression. Let's now put all of this together, right? Let's put all of this together. 1.3 times 1,000 times that number minus 100 times 0.25. All of that divided by 1 minus 1.3. Your answer is 75, or rather negative 75.9692. So you might say, hala, this is the wrong answer. Well, before you say anything, right, let's try and see if this is the correct units we're talking about. P2, or rather P2V2 and P1V1, or rather, sorry, PV slash in here is has just the units of kPa times V slash, which is meter cube per second. If we know what a kPa is, that is just a kilonewton per square meter. There are 2 copies of square meters in here. There are 3 in here. Cancel. You will be left with a meter. A kilonewton meter is just the same thing as a kilojoule, and a kilojoule per second gives us a kilowatt. So this is correct. However, look at this. Isn't this a problem? No. Because, right, your compressor is supposed to receive work. It's supposed to have work in. That is why it's negative, right? So this is our correct answer, right? This is our correct answer. And then now, this at the very least is done. Good job. What is your KE? And then what is your delta H? I will leave KE for last because it's very frustrating. Delta H. Okay, delta H. How are we going to get here? Right? We are going to just do delta H is equal to m dot times H2 minus H1. If we remember, wait a second, this is air we're talking about. So, again, this is just MCAT. MCP T2 minus T1. Do we have m dot? Actually, that's something that we, oh my gosh, we skipped all the way from the start of the problem all the way up to WC. Just goes to show how nonlinear things can be, right? And I will show you actually another way how to solve WC later, right? But we actually don't have a value of m dot first, so maybe we want to go through that first. Where are we going to get our value of m dot? Well, it looks like here you have a temperature, pressure, and a volume. No better place for us to just calculate, right? Okay, let's get here. PV equals MRT means that this PV slash is equal to M dot RT also works. In this case, your M dot is now equal to P1 V slash 1 all over R times T1. This is going to be 100 kPa times 0.25 all over 0.2871, and then you will have 300.15 Kelvin. You know, everything in here would have been much easier if I were just a little bit more lazy. I would remove the 0.15. But anyway, 100, 0.25, 2871, 300.15, you'll get an M of 0.2901. Okay? An M of 0.2901 kilograms per second. Okay? That's already something. And then now, notice that we have basically gone through many different things in a very interesting order, right? So we've basically solved C first, and then B first, and then I have a feeling then A next, and then D last. It's very interesting. Now we will go to D2. Well, where are you going to get D2? Well, you're going to use that for your area 2. And where else will you get area 2 except for your velocity at state 2? Basically, your state 2, right? Okay. Where are we going to get it? Well, using the continuity equation, right? The continuity equation states that your m dot is equal to rho 1 a1 vel 1 is equal to rho 2 a2 vel 2. We are supposed to find out this value of a2 so that we can find the diameter at state 2. We have a vel 2, right? You have a vel 2, and then we have a rho 2 as well. What do you mean we have a rho? Oh, well, actually, we don't have a rho 2 yet. Notice we can just turn this into pirata. Right? Notice that we can just say m dot is equal to p2 a2 vel 2 all over rt2. Why can't I say anything about this? Right? Technically, P2 we have an idea about, right? P2 we have an idea about, that is 1000 kPa. Your vel 2, yes, we do have an idea about. Your R also we have an idea about. What about your T2? Well, if you have a T1, a P1, a P2, and you want to find T2, we will invoke the very memorable mnemonic, which is T2 pe P2 cake. Right? Or rather, in this case, because this is a polytropic process, T2 pe P2 nin. Right? It comes in the form of T1 over T2, T2, and then it goes P, P2, and then nin, n minus 1 over n. But in this case, I would like to make it and just flip the 1 and the 2, right? Flip the 1 and the 2. Why is that the case? Because I find that it's better that the 2 is on top, because I can just put the T1 here and we can get immediately our value of T2, which is T1 times P2 over P1 raised to n minus 1 over n. So that means that your T2 in this case is just 300.15. And notice that in this case, we are looking at two different temperature readings. We are getting the ratio of the temperatures times, look at this P2. It's just 10 times P1 over P1. So cancel. Right? That is why I wanted to keep it that way. That is going to be raised to 1.3 minus 1 over 1.3. You will have in here 300 times 300.15 times 10 raised to 0.3 divided by 1.3. Your T2 in this situation is 10.31.3. Your T2 is 510.63 Kelvin. Okay, so that is your T2. And okay, that means that you have T2, you have your m dot as well. You're able to get for A2. And if you want to go directly to D2, well, we can do that as well. We know that your m dot is now equal to rho 2 vel 2 all over RT2. And you know that your A2 is just pi over 4 times D2 squared. And again, we do the same thing that we've done earlier. And then let's go ahead and square root immediately, right? You will have your big square root right here. You will have your m dot on top, which is the 0.2901, if I'm remembering that correctly, right? And then you will have everything at the bottom. So you'll have pi times your p2, which is 1000, if I'm, yeah. So times 1000 times your velocity 2, which is 70, all over your 4 times, right? Your 4 times 0.2871 times your T2. Your T2 in this case is 510.63. There you go. So we can put all of this in our calculator. What is our D2? 0.2901. Is that right? Yes, it is. All over pi times 1000 times 70 all over 4 times 0.2871 times 510.63. We will get an answer of 0.0278. 0.0278 meters. You might say to yourself, okay, that's quite small. But the thing is, the exit diameter should be in cm. So we slide our decimal place 1, 2. That should be equal to 2.78 cm. I think that is enough. Okay, 2.78 cm. And now the last bit, right? The last bit should be your Q. But actually, I will tell you guys about another kind of version of work steady flow that we can actually access, right? If you thought about this earlier, if you were trying to do this step by step, so first you want to get D2, then next you want to get M dot, next you want to get WC, most likely what you've computed first will be T2 instead of V slash 2. Is there another way for us to solve our our steady flow work? Yes. Although it's still here, the thing now is that we are in the presence of an ideal gas. So all of your P2 or all of your PV slashes become M dot RT. Right? So your work steady flow N times P2 V slash 2 minus P1 V slash 1 all over 1 minus n is equal to just n times m dot RT2 minus m dot RT1. Okay? And then in this case you will have 1 minus n. And then you will see that you can actually factor out the m dot and then the r. N m dot r. And then actually you can factor out the T1 as well. T1 all over 1 minus n. So you're like, wait, actually you can't. But yes, I can. I can force it to. What do we mean force it to? Look at this. We will just have on the first one, T2 over T1. Because notice, if you collapse them back, you will just cancel the T1s. You will be left with a T2 at the top. Minus 1. Now you might be wondering, why am I doing this? Why am I making it so much more difficult for myself? Actually, I'm making it easier for myself. What do you mean? Where else have we seen this before? It is here. Or sorry, here. So, what we're seeing in here is that we can substitute them and we will get n times m dot times RT1, right? All over 1 minus n times the P2 over P1 raised to n minus 1 over n minus 1. That is your polytropic steady flow work, huh? Polytropic steady flow work. If you want, this is very important, this is a very important formula, I can tell because I'm teaching the third years and we are using this equation still. Right? You might want to remember this, right? This is the steady flow work equation for a polytropic process, right? The thing about this is that if we plug in everything correctly, we should go back to the same answer from here. right? Let's try it out. Right? We will have 1.3 times your M, which is going to be 0.2901 kilograms per second. And then your R is going to be 0.2871 kilojoule per kilogram Kelvin. And then your T1 in here is going to be 300.15 Kelvin. Again, notice that we are looking here at absolute values, huh? Because we are dealing with ideal gases in the first place. All over 1 minus 1.3 can cancel, 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 cancel. You will see kilojoules per second, kilowatts. Okay, and now notice P2 over P1. We've been seeing this since earlier as well. P2 over P1 is just 10 times P1 all over P1, which is just 10 raised to 0.3, or rather 1.3 minus 1 all over 1.3 minus 1. So you can actually put all of this together. Let's see what happens. Hopefully, I don't embarrass myself. 2901 and 2871, 300.15, 1 minus 1.3 times 0.3, 0.3 minus 1. The answer for this should be just the same, right? Just the same, which is negative 75.9656 kilowatt. So that is your answer. You can see that the errors are really low. Okay, errors are really low, but finally, we now are able to go into your Q. Okay, how are you going to get your Q? Well, we need your delta H. It has our delta H been ano yet? Oh, not yet, right? Okay, we can find our delta H. Okay, there you go. Delta H is just going to be m dot times H2 minus H1, but again, right, we don't care about this because we are looking at an ideal gas. We can just turn it into m dot times Cp times T2 minus T1. Okay, so in this case, we already have a value of m dot. We know the Cp of air, and we know T2 and T1. We can solve for a value of delta H, which is going to be 0.2901, and then your Cp is 1.005, and then your T2 and T1, well, I forgot to translate your T2 back into, where's this? Where is your T2? I forgot to translate back it into degrees Celsius, so it'll just stay that way at Kelvin. So 510.63 minus 300.15. Notice that this should also be, right, kilograms per second, kilojoules per kilogram Kelvin, and this is Kelvin. Cancel, 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 cancel. This is now kilojoules per second, right? Or which is kilowatts, right? So that is your delta H. Let's see what's happening in here. $61.3655. 61.3655. This is now in kilowatts. And so finally, I'm saving the best for last. What about KE? Because technically, we can already solve for KE. So you're like, no, we can't, right? KE in this case, or delta KE, in this case, is going to be, right? We said 1 over 2,000 so that the students can learn that this is already in kilowatts, right? M dot times vel2 squared minus vel1 squared. The thing about this is that, yes, we know the value of of m dot. We know the value of vel2. We don't know the value of vel1, but actually, we kind of are supposed to know something about this. A compressor, if if you're going to look up a compressor, right? Gas compressor, right? Gas compressor. There you go. Oh boy, I'm reliving the negative memories about this thing. The thing about this compressor is that it takes in air from the atmosphere. Okay, so if it doesn't ring a bell yet, or if you don't understand the implications of that yet. Okay, we'll find out very soon. But basically, these compressors, they take in air from the atmosphere. They take in ambient air. So you're like, okay, well, what's so wrong about ambient air? Well, it's at atmospheric pressure, sure, whatever. And the thing about ambient air is that, well, it's not moving, right? In Tagalog, we have this phenomenon called kulob, right? What's basically happening is that the air is not moving, right? So therefore, you have that little smell that you understand, like when you come into a house that has not been ventilated for a long time, right? That is your what do you call that again? That is your kulob. What I'm saying in here is that this compressor takes in ambient air, ambient slow air. What I mean to say is that your vel 1 is negligible. I understand it's not zero, but in this case it is negligible because it is so slow compared to your velocity at state 2. Right? So no, just a little note. I know that your vel 1 is not just 0. But vel 1 is very small compared to vel 2. So that is why we want to make it negligible. So congratulations, we now already have the value of delta KE. We're just gonna have to put everything together. So, well, how are we going to do this now? Your Q is now equal to, if we put the W to the other side, W plus delta KE plus delta H. We will have W, which is negative 75 point, what is this? 9656 plus your delta KE, which is just this thing. Let's just try to put this all together. 0.2901 divided by 1000 times 70 squared. You'll get 1.42149, so 1.4215. 4215 plus your delta H. That will be, what was that again? 61.3655. So if we put all of this together, negative 75.9656 0.4215 plus 61.3655, we will get an answer of negative, which is, of course, I think this is hopefully what you guys were expecting as well. It's a heat loss, right? Negative 13.1786 kilowatts. That is your answer for the heat loss in here. So that means that your compressor is actually losing heat. And a lot of the things, right? A lot of the things, if they're imperfect, they will always lose heat. Right? This is one important form of energy. Okay? Sorry, this one important form of energy transfer, not energy stored energy. Okay? So there you go. That is your problem 6. And now there's just a little thing that, oh man, problem 5.7 is going to be next, right? We see here that we had a little bit of a roundabout kind of way of solving this. I was able to show you guys 2 different ways how to solve for your work of compression, right? And then basically it's kind of the same, right? So there's no worries there, right? And there you are also seeing in here the heat loss, right? The heat loss is almost always going to be negative. Okay? Because it's a heat loss, right? It's going up. There you go. Right? That's what I wanted to say. Okay? Now, with problem 5.7, you might see a little bit of a problem. Okay? A pump is used to carry water flowing at a rate of 1.5 kilograms per second to a reservoir 15 meters above the suction side, which has a pressure of 3.0, right? 3 bar absolute. Suppose atmospheric pressure is 1 bar. So you're like, oh gosh, why did they mention the suppose atmospheric pressure is 1 bar? If the water temperature remains constant, the water temperature remains constant at 25 degrees and that the changes in kinetic energy are negligible, A lot of things are going to be thrown up into the air. You're like, what? What? Right? How much power should we provide the compressor? Or rather, the pump, right? In this case, the pump. Okay? Okay. Let's try this out now. There is a special, right? There's a special symbol for a pump right here. So let's just draw it right now. So when you're talking about a pump, you're only talking about a liquid-based fluid mover. So pump is going to be like this, and then you're going to go and draw the state 1, the state going inside the circle, and then state 2 will be going on the surface, right? It's going to be tangent to the circle, and then it's going out. And there is also a stand that it's also using to be off the ground. So if you see this, it's gonna be a little bit ridiculous the first time you see it, but well, it's you learn to love it, right? So a pump is used to carry water flowing at a rate of 1.5 kilograms per second. 1.5 kilograms per second. Okay, to a reservoir 15 meters above the suction side. So actually, I totally forgot about the 15 meters. So let's just have this line right here, and then there you go. That is your state 2. There is in here an altitude difference, right? An altitude difference here of 15 meters. Okay, 15 meters above the suction side, which has a pressure of 3 bar absolute. So apparently, in this case, your P1 is 3 bar absolute. Okay, so this is water, but why are they saying absolute? This is kind of confusing already. Right, 3 bar absolute. Okay, suppose that atmospheric pressure is 1 bar. Okay, well, what does that mean, right? What does that mean? The thing is, a reservoir, you might say it's just a word, right? It's just a filler word. The thing is, a reservoir is a literal tank of water. Tank of water, we're talking about like a big tank of water that is open. It is open to the atmosphere. That is where they're pumping out the water. So the water is going out in here, and it's open to the atmosphere. That is the little clue that you're going to have to notice in here. Your P2 is now open to the atmosphere, which is technically 1 bar. Okay, so now you're like, oh my gosh. All right. If the temperature of the water remains constant at 25 degrees Celsius, it might seem like you are being led to the conclusion that you are experiencing an isothermal process. So you're like, that's that I don't know, right? If the water temperature remains constant at 25 degrees Celsius and the changes in kinetic energy are negligible, let's just try it now. How much power should we provide the compressor? Right? This thing. So this is your WC. How much power should that be? And well, let's look. Q minus W is equal to delta KE plus delta PE plus delta H. Okay, let's think about this now. Of course, there's W, so you can't cancel that. What about Q? I don't know what to do with that, right? Next, your KE is 0 at the very least. Okay. And then your PE is something now that we should actually think about. Like, what does that mean? What does your delta H mean? Right? If your T is isothermal, right? Oh, sorry. If your T remains at 25 degrees Celsius, what is happening? Right? What is going to happen in here? The thing now that's supposed to happen in here is, if we think about it this way, this is a pump. This is a pump that is supplying liquid. Okay? It's supplying liquid. That means that if this liquid remains at 25 degrees Celsius, let's ask ourselves, is there heat transfer? Right? The water did not get hotter. It did not get colder as well. So, well, it just remained at 25 degrees Celsius. Is there heat transfer? You will be poised to say, you know what, actually, no, there's no heat transfer. So we can cancel it out. Okay? And then now what's going to happen? Right? Now what's going to happen is, well, you're going to see now this work this work of compression, you're gonna have to compute it using PE and H. And now you're saying, wait a second, why can't we just use your W, right? Your steady flow work for an isothermal process? Good question, actually. The thing about this is that this is actually not isothermal. That is only an approximation. Technically, a lot of the things in here are going to remain constant as well. It's because, well, you're looking at water. Let's look at pressure 1, temperature 1. Pressure 1 is 3 bar, temperature 1 is 25 degrees Celsius. What do you think that is? Right? If we're going to look at our thermodynamic property tables, if we look at our water, say for example at 3 bar, the saturation temperature is 133.6. This is much lower, which means this is a compressed liquid, state 1. All right, sure. What about state 2? Right? Pressure of 1 bar, 25 degrees Celsius, it really does not matter. 1 bar has a saturation temperature of 99.63. This is still another compressed liquid. This is literally just a pump that is pumping water. And so now what? Right? Now what? Well, the thing that you should now think about is, right? Let's look at this another way. Right? Another way is this delta H. There's something wrong with it. Or at the very least, I'm not saying that there's something wrong with it. It's more just like, we can break this apart, right? If you remember from earlier, right, your H is equal to U plus PV. And so that means that your delta H is just equal to your delta U plus your delta PV. And again, we see, there is no change in temperature. Therefore, there's no change in internal energy. So cancel, you will now get in here delta of PV. So what is delta of PV? Well, think about it. It's just going to be, let's rewrite everything now. Negative W is equal to PE. So this is going to be mg, right? Z2 minus mg Z1. Right? Dot. And because this is a potential energy, let's just look at the units. Let's look at the units. This is going to be M. And then this is G, meter per second squared. And then this is Z, M. Right? So M, G, and then Z. Let's see what's going to happen, right? We will have in here kilogram meter per second squared, mass times acceleration. That is going to be Newton. Newton times a meter is a Newton meter or a joule. And a joule per second is actually a watt. So that is not right. So what you're supposed to do is turn it into kilowatts. That is why instead of just doing this, we turn this into division by 1000. And now notice, what is your delta PV? What is your change in flow energy? That is just going to be your P2 V/2 minus P1 V/1. Oh, yes, Nicola. Okay. Yes. Hello. He's hungry. So if you guys are hearing some meowing, he wants food, but it is currently an unspecified time in the evening. Okay. All right. Now let's look at this. Let's see if this is indeed in kilowatts. But actually, we have looked at this earlier, which is this thing, right? Your P2 V/2 is just here, right? Your kilojoules per second, that is now kilowatts. Okay, so let's go back here. Everything in here should be in kilowatts. Okay, now let's try and analyze, see if we have values for different things. M dot, we do have M dot, that is 1.5 kilograms per second. We have a G, of course, right? And the thing is, we don't have a value of Z2 or Z1, but when we smash them together, M times G over 1000, and then you will see in here, Z2 minus Z1, I know the relationship between state 2 and state 1. I know the difference in elevation of Z2 and Z1. That is your 15 meters. Right? Notice that in this case, your state 1 in here, or rather your state 2 is 15 meters taller than your state 1. That means that your Z2 minus your Z1, the difference between them is 15 meters. So I know all of the values in here. Do we know all of the values in here? P2 V2 slash minus P1 V1 slash. I know P2 and I know P2 and P1, but there's nothing in here that makes me think of V slash 1 and V slash 2, unless I make that a small letter. What do you mean, make that a smaller letter? Well, these are big letters, right? V2 and V1. What if I turn that into M dot, oops. What if I turn that into M dot V2? What if I turn this into M dot V1? Okay, let's try it out. If that's the case, then you will have in here M dot G times delta Z all over 1000. And then you will have in here, I can group out the M dot, and then you will have your P2 V2 minus your P1 V1. Because we found out that states 1 and 2 were both compressed liquids, right? We can actually get the values of V2 and V1. Very interesting. We now have a to-do list for some reason, right? So your V1 and your V2, we're just going to have to approximate. Your V1 is equal to your VF, right, at the same temperature, which is 25. But wait a second, we just said that the temperature remains constant at 25. Therefore, your V2 is also the same thing at 25 degrees Celsius. So both of these things are going to be the same, and both of them are going to be your VF at 25 degrees Celsius. Your 25 degrees Celsius apparently in here is this thing, 1.0029, right? And because it's VF, you need to divide it by 1000 meter cube per kilogram. And so actually what you can do is you can also factor out the V. Okay, very interesting. And mg delta Z all over 1000. And then now you're going to have m dot V times P2 minus P1. Does this ring a bell anywhere? Right? Does this ring a bell anywhere? It should. Right? Notice that m dot V, you can actually put that back into V slash. Is this now a little bit more familiar? Right? It should, because just in our part 1, if we're going to scroll back all the way here, look at this. Negative V times P2 minus P1. Oh, that's the steady flow work for an isometric process. Right? So a lot of things are going to parang smash into each other very, very complicated fashion. But the thing about this is that, well, what we're doing in here is an isometric process actually. So you're like, huh? Where did that come from? Right? How did an isometric process come into view in here? I just thought that earlier we were talking about an isothermal process, and now you're telling me it's now an isometric process? Well, yeah. So the thing about this is that this is a pump, and a pump is bringing liquids. The thing about liquids is that they are called, we call incompressible fluids. If it's incompressible, the line of logic is as follows. If it's incompressible, you cannot compress it. If you cannot compress it, you cannot change its volume. So the volume that is occupied by your liquid at state 1 is still the same volume that is occupied by your liquid at state 2. In other words, this is an isometric process that just happened. Oh, I see. And it is completely possible for an isometric process like this to have no heat transfer because there was no increase in temperature, right? So, well, nothing else to do, right? So that is going to be the process. That is how you're supposed to think about this, right? This is how you're supposed to think about this. So, well, let's now put everything into effect, right? Your m dot is going to be 0.2901. 2901. Your g is 9.81. Your delta z is 15. And then you divide everything in here by 1000. Next, right? Your m dot is 2901. Your v is 1.0029 divided by 1000. And then your P2 and your P1, well, your P2 is 1 bar, or, right, in this case, 100 kPa minus your P1, which is 300 kPa. So you might be thinking, why kPa? Okay, let's just have a little go at the units, right? Kilogram per second right here. And here, this is meter cube per kilogram. And then, this is going to be in kPa. So you might be wondering, okay, kPa, go ahead. If we're going to, right, if we're going to expand this just becomes kilonewton per meter squared. So we can cancel, and then cancel. You'll have in here an extra m. Kilonewton meter is a kilojoule, and then a kilojoule per second is a kilowatt. Everybody in here is a kilowatt. And so we can put everything together. We will get 0.901, 1.0029, 1000, 100 minus 300. We will get an answer of, oh boy, we will get an answer of, well, okay, WC is negative 0.0155 kilowatts. Apparently, right? The thing about this is that, yeah, this is small. And you might be wondering, like, why is this small? It's because, let's look at everything again. Let's look at everything in a more, how should I say this? In a more interesting light, right? Everything in here is actually, wait a second. Wait a second. Huh. P2, V2, P1, V1. What? Wait a second. This is too small. Okay, now this is my reality checks coming in. Oh, I know. Oh my gosh. I had a slide for this. There it is, right? Usually negligible. You have your pump in here. You have your enthalpy. You have your enthalpy going out, and this is your pump work. And then, if pumps move liquids, compression is approximately isometric, which means that your pump work is that. Your pump work is that, right? And that is immediately our answer na pala, right? So, okay, there it is, right? And the thing about this now is that that's only for a change in elevation. Oh, sorry, that's only for a change in pressure, right? So, I mean, like, it is kind of correct, right? If there is no change in elevation, I suppose this negative W would be equal to, if there is no change in elevation, that would be M times V times B2 minus P1. Yeah, this would be negative V slash times P2 minus P1. So, okay, apparently, the thing is though, why are they working against each other? You know, why are they working against each other? Your P2 is 1 bar. Oh my gosh, I misread every I misread everything. A pump is used to carry water flowing at a rate of 1.5 kilograms per second to a reservoir which has a pressure of 3 Okay, never mind. Sorry, guys. So this is 3 bar, and this is the one that is at 1 bar. There you go. That's why I was wondering. So this is actually just 300 minus 100. This one is the one that's open to the atmosphere. Oh boy. You know what? I feel like I'm gonna have to redo this. But anyway, let's address this now. 0.2901, 9.81 times 15 divided by 1000. 0.2901 times 0.0029 over 1000. 200 now. There it is. Yeah. That's much better. That's much better. That is going to be 0.1009. Yeah, kilowatts. That's better, right? I was wondering, because okay, all right. Oh my gosh, now I'm rattled now. The thing about this is that I know that this is correct because if you think about it, this is 100.9 watts, right? And if you think, and if you look at the wattage of like some certain water pumps, you will see that it is about this value, especially if you are moving 1.5 kilograms per second of water. Again, 1.5 kilograms is the same thing. 1 kilogram is 1 liter of water. So this is just like 1.5 liters per second of water. You're moving it through this pump, right? And you're pumping it to a pressure of 3 bar. Okay? So in this case, you might say to yourself, well, that's not a lot of energy. Yeah. Number one, it's not a lot of energy because you're only moving liquids. Right? Liquids, you don't have to compress them, right? You don't have to compress them. You're just going to have to get them to a higher elevation, usually through a water tower, right? And usually you're also just going to compress them, not compress, but just raise their pressure a little bit. Right? So that's what pumps are used for. Okay? So we were able to, right, in this example, right, we were able to get the derivation for your pump work. Your pump work in here, if nothing else is being given, is negative V slash times P2 minus P1 because of the fact that this is isometric. Okay, so a lot of red herrings, right? A lot of red herrings. Seems to be isothermal. It kind of is, kind of isn't, right? The actual process that we need to follow is that of an isometric process, right? Maybe I'll post a little supplement to this, right? A little document that you might want to read just so you know what has happened or what's supposed to happen, right? But just a little summary, right? A little summary is that I got this wrong. Sorry, I read this wrong as the one who's always trying to say, guys, please think critically, you know. Whoops, that is my mistake. I'm sorry. Right? Okay, just for a little summary, right? We were able to say that okay, if this is isothermal, then there's no change in temperature and there is no change in internal energy. So just like what we did for the pipes before, we can cancel out the delta H and replace it just with delta PV. Interesting. And then you will basically have your delta PE in here because, well, there is an elevation difference, right? Which is now this. Now, we will get here a delta PV, which is just P2V2 minus P1V1. But the problem is we don't know our volume flow rates. So, what if we were able to turn them into M times V? And apparently, yes, we were able to turn them into M times V. Now, we're saying in here, oh, okay, I can just get these from the tables, right? And apparently, because they are both compressed liquids, they are both pulling, right? They're both getting from the same temperature, which means V1 and V2 are roughly the same, which means that you can actually factor out the V2 and V1. You will have your M dot V times P2 minus P1. And if this were not in here, you will have negative WC is equal to so on and so forth, which gives you this thing. The work of the pump, right, is just your isometric steady flow work, right? And again, it's isometric because this pump is carrying a liquid. A liquid is incompressible. If you can't compress it, you can't change its volume. So it's isometric, right? So there are a lot of hoops that we need to jump through for us to get to that final bit of information. But there you go. Whenever you see another pump, right? Whenever you see another pump, just remember, okay, this is pumping a liquid, right? This is pumping liquid, and a liquid usually cannot be changed, or rather, a liquid's volume cannot be changed. So isometric. Okay. All right. Now that we have that, the problem is in here, there is still a temperature, or sorry, there's still an elevation difference. So there's a little addition to everything, right? There's a little addition to everything. If actually this were removed, what would this be equal to? If that were removed, oh, the power consumption would have only been 58 watts. So that is also substantial. Now that it's been clarified, right? So this is going to be our answer, right? Power consumption that we need to feed to the pump is 100.9 watts. Okay, that is your problem 5.7, right? So very confusing, but there you go. And I believe that's it for pumps, right? That's it for pumps. Next, we will have heat exchangers, and we're almost out of the woods. This is actually the last question for, next question will be the last question for topic 5, and then a little bit for the supplement at the end, right? Throttling devices. I will have an additional question there as well. Okay. So if you guys have any questions, please let me know, and we will continue and conclude this steady flow devices series. So see you then. Thank you very much.